All right, we'll get going here. So hello, thank you for joining today's webinar on the treatment and recovery of nitrogen and ammonia in digestates. I'm Paul Green, and I run an R&G advisory business. I hold these free monthly webinars for their educational value. Over the weekend, you'll get an email with links to download the slides from today's presentations and a copy of the video. Today's agenda, I'm going to open it with talking a little bit about nitrogen-based fertilizers and the behavior of ammonia. Next, we're going to hear about ammonia stripping from Biosis, and we're going to finally hear from POC about Animox. Let's talk about ammonia a little bit. So NH3 exists as ammonia mostly at elevated pH. Very pungent odor, likes to volatilize. It's an unstable molecule. It's not happy in a liquid solution. Toxic to fish, aquatic species, and rivers, and can be toxic to methanogens. At a lower pH, it exists as ammonium. Adding acid keeps ammonia in the ammonium state. It's not as volatile, and it likes to stay in aqueous solutions. Sources of ammonia largely attributed to the breakdown of proteins in things like digesters and in landfill leachates. So the protein molecule always has nitrogen in it and will give off NH3 and H4 on its degradation path. Typical digestate, you'll see this digestate had about 2,600 milligrams per liter of nitrogen. This is a food waste project at 1% total solids. So of that total nitrogen, about 90% of that would be ammonia. What do you do with ammonia? You can mainly recover it or you can destroy it. We can recover it as a value-added fertilizer. Aqueous ammonia is pure ammonia in a water solution. Ammonium nitrate is ammonia reacting with nitric acid. Ammonium sulfate is ammonia reacting with sulfuric acid. So you can destroy it or you can convert as in another form as done in the wastewater treatment world through denitrification systems to make a nitrogen gas. So it's really your first pivot point. Do I recover my ammonia or do I destroy it? Some other things to think about as you look at recovery. A fertilizer off-taker is looking to purchase the fertilizer. Long-term contracts can be hard to find. Getting a price that you can count on can be challenging. Getting the right criteria for what your constituents are going to look like is hard work. Inventorying materials is challenging. Farmers typically need the fertilizer just a couple times a year, so material handling is always a big issue. Organic versus inorganic nomenclature. Everybody would like it to be organic due to the price premium, but anytime you add synthetic chemicals to the mix here, it would keep it from being labeled as organic. When you destroy the ammonia, you need to look at your long-term viable partner to take the water, such as your sewer authority. It can be more reliable to destroy it and discharge it, but it's not as glamorous of a story. So things to think about when you do recovery: lowering the pH, make it more acidic, like adding HCl, releases hydrogen ions into the solution to drop the pH to drive it towards ammonium. Raising the pH, making it more basic, will drive it towards the ammonia stage. Reactions during scrubbing, you'll hear about more. Ammonia is the base. Things like nitric acid can be the acid, and you're making ammonium nitrate from that reaction during the scrubbing. Same thing happens with the sulfate if you're adding sulfuric acid. Strength of recovered ammonia is pretty critical. In the digestate, you're only at about 0.2, 0.3%, but farms are used to things like urea that are anywhere from 30 to 35%. So land spreading digestate nitrogen, it's very dilute compared to what farms are more commonly accustomed to. So in this pH scale, it shows the behavior of ammonia. So at a low pH, you'll see that there's very little ammonia, and the nitrogen exists all as ammonium. As your pH increases, you'll see that suddenly your ammonia exists, much more unstable, much more odorous, and your ammonium is much less at the elevated pH. Different ways to remove ammonia. We're going to talk about stripping and recovery. Membranes can work, evaporation, drying, ion exchange. Biological treatment systems are viable. We're only going to talk about Animox today, but there's many other denitrification systems you can look at. Other systems include worm beds, algae reactors, lots of ways to go about this. Certainly many things to watch in your digestate, including hardness, alkalinity, suspended solids, other organics, as you look to design a proper long-term solution. You'll hear about fertilizer naming. It's a 3-digit name, NPK. First number is percent active nitrogen, second is active phosphorus, the last is active potassium. So like this malorganite you see here, 640 is a way we would name this fertilizer. Aqua ammonia is a commonly used fertilizer. This case, this particular product is a 2000 pure ammonia in water, but it's very volatile. It's hard to apply on plants. It's hazardous, and a lot gets volatilized. So with that, I'm going to hand off to Jan Vandenbroek. Jan is the managing director and co-founder of Biosis. He has a background as a chemical engineer. He's held several engineering and management positions at companies like Fluor, Engie, and others before starting his own engineering consultancy firm that later became Biosis. Biosis focuses on resource recovery solutions from wastewater, such as digestate from agricultural, industrial, and municipal sites. The company has a global reference list, and in 2022 was purchased by Nyhouse Sour Industries, and since then has rapidly expanded into the US market. So Jan, with that, the floor is yours.
Thank you, Paul. And your pronunciation is very, very good, actually.
Okay, good.
I hope you can see my screen.
Not yet?
Not yet.
Okay, it's coming.
Now you can, huh?
There you go. We're good. Yes, we have it.
Yeah. All right. So my presentation is about managing nitrogen in digestate. And who are we? Well, we are Nyhouse Sour Industries, and Nyhouse Sour Industries consists of several brands, and I represent Biosis. As Paul explained, I'm the founder of the company, but I'm also the managing director now of Biosis. And we have all these brands. Two of them are US-based, Natural Systems and Aquachem. And we closely work together with them. So what we try to do as a group, we try to close the water loop. So anything from reduce to remove, reuse, and recover. That's what we offer technology for. I mentioned that we are represented in North America through regional offices, and those are based in New Jersey, where the head office of Natural Systems is, and in Tennessee, where Aquachem is based. We have several references in the US at the moment. Not all in operation, but some are under construction. We have a project in Latin America, and most projects that we do are in Europe. The company was founded in 2009, and we were purchased by Nyhouse in 2022. And we are a Dutch company. You can probably hear it from my accent. And but we worked closely together with the teams in New Jersey and Tennessee. So something about ammonia stripping and recovery in general, and specific about our technology. So as many of you know, there are the two general principles of stripping technology. One is air stripping, the other one is steam stripping. The air stripping is called so because air is the driving force, and steam stripping because steam is the driving force. In most cases, an alkaline agent is being used to increase the pH and shift the equilibrium, as Paul explained, from ammonium to ammonia. And the difference between the two is that in the air stripping, typically an acid is being used to capture the ammonia as a salt, like ammonium sulfate or ammonium nitrate, in the case nitric acid is being used. And in the steam stripping technology, the ammonia is condensed and captured as ammonia water. So we Biosus uses the air stripping technology. What Paul explained is there's an equilibrium between ammonia in the gas form and ammonium in the vapor and the liquid form. That is also a function of temperature, apart from pH. So typically, what you see is that companies applying stripping technology, they increase the pH, but you can also operate at an I hope you can see my pointer, at an elevated temperature, and you have the same effect. So in that case, you would have, instead of operating at the pH 10, you would be able to operate at pH 8 at elevated temperatures like 90 Celsius. So stripping is depending on temperature, it's depending on pH, and it's depending on the airflow. And in all cases, higher is better. But it is also depending on the residence time, which is a factor for us as a technology provider. And it's a factor depending on the alkalinity, the viscosity, and concentration, and whatever. This is how our system looks like. So it's, in this case, the standard is a 3-stage column, where a substrate is being heated up to temperatures of roughly 80 Celsius. Sorry, 80 Celsius. I cannot convert it directly into to Fahrenheit, but I hope you understand. And it enters the stripper. It falls from the top in the stripper to the bottom. The bottom, it's still close to 80 Celsius, so that temperature can be recovered to heat up the incoming substrate. And then the air is brought in countercurrent modus with the digestate, and the air is enriched with ammonia, is sent to a 2-stage scrubber, and then recirculated again by a main fan, and that is the main electrical consumer of the system. There is a small bleed stream because you want to prevent the buildup of undesired components. And in the main scrubber, we add water and acid, and we operate it at a temperature of pH 2.5. And what we do is we send a little stream to the middle column that we call the neutralizer, and there we neutralize it to a pH 7 product. That is an option. You can skip the middle column, and then you get an acid product. What are the USPs of our technology? Well, we don't typically need an alkaline agent. We can, but in case of working with digestate, you don't need to. It has a low energy consumption, both electrical and thermal. We have a high tolerance to pollution. Actually, the system was developed initially to operate with unseparated digestate, and it still can do, but in most cases we operate after a decanter. But apart from that, we do not need any pre-filtration. It's compact, minimal, and we use standardized units that we can configure to order. So in that case, we can do any throughput or any stripping efficiency that a customer wants. It's reliable, easy to operate, and it's nearly closed loop. There's a very small bleed stream, but that is almost it. And if you apply it instead of a biology, it has a better carbon footprint than any biological system. So it is possible to produce a pH neutral fertilizer, and we standard can offer an automatic cleaning system for the stripper and for the heat exchanger. This is the situation when you have where you skip the middle column, and you can do that if it's not relevant that the pH is acidic. In this case, the pH is close to 2, and in the other situation it's around 7. The product that's being produced is a liquid product. In case of using sulfuric acid, it's ammonium sulfate with approximately 40% dry matter concentration, but still a liquid because it's very good solvable. And on the left-hand side, you see a graph where you see roughly that above a certain dry matter concentration and below a certain temperature, you get a crystalline form. And in our process, we like to we like to stay below that line. So the maximum you can get is roughly around 42% of dry matter, which would be equivalent to 8.9% of nitrogen. In case you use nitric acid, you have a product called ammonium nitrate, and then you can go to higher nitrogen values. But of course, you have to use nitric acid. That is, generally speaking, more expensive than sulfuric acid. Well, what you can also do is, as they are liquids, you can blend the two, ammonium nitrate, ammonium sulfate, to get a product that might have a better agricultural value. In Europe, we are able to trade this fertilizer under fertilization product regulation. And we are also working on innovations that are in a final stage of development, but not yet commercialized. And those are we can produce an ammonium bicarbonate solution 7 to 8% using CO2 as binding agent, and we can also produce ammonia water 20 to 25%. We're also working on technology to crystallize to solid salts. And typically in these situations, heat is needed, but we are looking at cool crystallization because that enables customers to have a crystallizer on a smaller scale, and typically that is what is needed for our customers. So if you look at the test results, I already mentioned it's an equilibrium between air that is driving around, and we measure that in electrical fan consumption and temperature. If we do not increase the pH, typically the pH of digestate is close to 8, which is enough. And what you can see in this picture is, and it should not surprise you, that the higher the temperature, the better the stripping efficiency is, and also the higher the amount of electrical energy being used by the fan, the higher the stripping efficiency is. So 80% is more or less what you can get without using an alkaline agent. In most cases, we do not use an alkaline agent because we work with digestate, and digestate has a high alkalinity, and you don't need it. And if you do, you need a lot of alkaline agent. But I will show you an example later where we do. So reasons why not to consider an ammonia recovery system. So typically, I would say there are several markets for ammonia stripping and recovery. So there's the wastewater treatment market, municipal, where you can think of the stripping process after a sludge digester, or an industrial process after an industrial digester, where you digest food waste or animal byproducts, organical fraction of municipal solid waste, sludge digestate, dryer condensate, whatever, or agricultural digestate. There's also a fourth market, but it doesn't work with the digesters, and that's not the subject today, so I will skip that. So what we see is most customers, they are looking for means to control the ammonia level, or they need to remove the ammonia in the effluent. Or they have a biology and they don't want to expand it, or they need the biology and they want it small. Small footprint, fast installation, easy to operate. Fertilizer production, the value of the fertilizer, that's mainly not the reason why customers choose a stripping process. Reason is, especially in Europe, that the value is not high enough. But why are customers interested? Because it enables you to have a flexible operation in terms of volumetrical load. It's a chemical physical process, so very easy to operate and easy to ramp up, ramp down. And it enables you to have a flexible operation in terms of nitrogen ammonia loads. Carbon footprint is also an issue, but not so much for industrial projects. We see that in Europe in the municipal sphere. Examples of agricultural digestate applications. Actually, you can use a stripping process in two ways. One is in a recycle modus over a digester, and the other one is end of pipe, meaning as final step or before biology. So in case of a recirculation processes, you can think of when you want to digest poultry manure that is very rich in nitrogen or maybe food waste. Typically, the max values for ammonium intoxication are 5 grams per kilogram or 5,000 ppm, 3 grams per kilogram for thermophilic operations, so 5 for mesophilic operation. And then recycle modus, what you want to do is you want to prevent the dilution with water, because if you do, then you need to store it and you have to spread it. That comes with significant costs. And in the other case, at end of pipe case, what you want to do is you have to need to reduce the ammonium load. And this is important. Ammonium is not equivalent to nitrogen. So typically 70% of the nitrogen is mineralized in a stripper in an ammonium form. That means that at 80% stripping efficiency, you would be able to reduce 56% of the nitrogen. So that's always something to bear in mind. But in some cases, it's really essential to do that, or it's the license to operate that we also see for this customer. So this is an example of an agricultural project in Italy. This customer is operating a digester, large digester with dairy manure, and they add fried chicken manure to produce biomethane that they inject in the grid. They also produce bio-LNG. And here we operate both to control the ammonia level in the digester, but also to reduce the ammonia load to the fields. And in this case, that is really a license to operate, because if they didn't have it, they were not allowed to operate. In this case, the installation removes approximately 75% of the ammonia. and no alkaline agent is needed. It operates flexible between 30,000 and 200,000 gallons per day. And for the customer, important is that they do not need dilution water, that they have the license to operate clearly, that they save costs while spreading the digestate, but also very important, that enables them to flexible operate the installation. So adding a little bit more chicken manure might be interesting to have more biogas, but you also add more nitrogen and you need to strip more. In an industrial and municipal digestate market, it's typically one of the treatment steps. So it's an end stripper of a thin fraction before, in most cases, biology. Why? Because you have fluctuating loads, because you want to reduce a biology. So you use the system as a peak shaver. It's a compact solution. It's easy to ramp up, ramp down, and in the municipal sphere also to reduce nitrous oxide emission or laughing gas, which, as you might know, is more than 270 times as bad as CO2 is. And compared to biological processes, a stripping process does not have any nitrous oxide emissions. So examples of these are, this is a project in the US. Food waste is being digested here, and the customer was looking for a robust solution, end of pipe, because they had to meet stringent nitrogen emission levels. In this case, we had a stripper before an MBBR and an optional DAF unit to remove the solids. Actually, the customer had to meet very low nitrogen and solid levels. In this case, as it is more or less end of pipe, we do add an alkaline agent to get 95% of nitrogen removal. Installation is approximately 100,000 gallons per day, and the benefits are that they have a reliable and flexible chemical process. They were able to reduce the size of the MBBR significantly. Another example of a municipal project in Germany, relatively small one, but here also this is an island where in the summertime they have 300,000 tourists, in the wintertime a tenth of that. So they need a flexible solution, and sludge from different municipalities is collected on a central location where it is digested and incinerated after a drying step. Energy is being produced, but the existing biology, they did not want to expand the existing biology. That's why they needed a flexible system to reduce the ammonia load. That is what it does. And besides that, it's a very nice example of circular economy, because the ammonium sulfate, in this case, that is being produced, is used by the farmers on the surrounding fields. So literally, they are tanking the ammonium sulfate at the wastewater treatment facility. It's scalable technology. In this case, you see 4 lines in series. It's very compact. This is an industrial site in Italy, but you see that it's very compact. Some examples of recent projects that we got. This is a municipal plant in Norway. After the THP, thermal hydrolysis process, in combination with technology from Cambi. This is in the Netherlands as a pre-treatment before a DAF unit. Why? To save chemicals. This is the same customer where we do the third project for in the US. Um, Maybe as a final slide, because I see you coming in, Paul. I think I used my time. We also have mobile units. We built those units to ship to customers to be able to demonstrate the technology. So you can use it. You can see if it works for you. And yeah, that's
Okay.
almost my presentation. Yes.
Thanks, Jan. We had some questions come in. I think maybe we'll stay a little late at the end and address them. So I appreciate that presentation, Jan. You've got a lot of very pertinent experience. You guys have been doing many, many projects. So thank you for your presentation. Again, the slides will be posted later this afternoon. So we'll let you go, Jan, and we'll bring in Timur Danayev from POC. So Timur is the managing director of POC Environmental Technologies, overseeing operations and growth across North America. He brings more than 20 years of process expertise in industrial wastewater and RNG applications. Timur has a doctorate in environmental engineering and is currently pursuing a doctor of business administration. His career blends deep technical knowledge with strategic leadership to drive sustainable, high impact solutions. So, Timur, the floor is yours.
Oh boy, Paul, thank you so much. Love to be in great company. This is an amazing venture and an amazing platform. So thank you so much for having me as part of this platform. Making sure my voice is coming through fine and the
Yes.
share screen is showing. Okay, excellent.
Excellent. Yes, all set.
Yeah, I love environmental engineering, and there is so many great ways to skin the cat. I'll just be talking about one more application, right? I'll start with a short introduction and then dive into the technology that I believe blends ammonium removal and some recovery as a resource. POX is part of an international conglomerate called Ski and Water. Ski and Water holds 14 portfolio companies and last year's revenue of 1.4 billion euros exclusively in the water and wastewater sector. We, as POX, also have offices all over the globe. And today I'll be talking about my neck of the woods, which is North America. I usually call it C2C, Caribbean to Canada. And we've been in the continuous operations in North America since early 90s. POX is, I believe, most well known for initiating and proprietary biological technologies in environmental sector. And the whole lineup that you see in front of yourself is, and I'm a student of environmental engineering, is an extremely impressive lineup over the years, starting with granular anaerobic technology, very first NMOX, which is the ammonia removal technology that we'll be discussing today, and then following by Thiopac, which is a biogas desulfurization technologies, all technologies based on environmental biotechnology and the innovations coming through that. Today, specifically, we'll be talking about nitrogen removal, and Paul, during his introduction, mentioned the conventional nitrification denitrification process. And NMOX fits neatly into that category. The development started with the Technical University of Delft, discovering a very specific subset of microorganisms. And then by 2002, the first full-scale NMOX process was installed by POX. And in fact, in North America, we fell so much behind the curve that by the time we tried to trademark our technology in North America, NMOX by POX has become synonymous with the technology itself. And so that complicated that step, but we're still obviously continuing to move forward. And to this day, as far as NMOX goes, we have the most amount of installation and treat the largest backset of ammonia using NMOX. The process is usually presented as a comparison to the conventional nitrification denitrification, which was what Paul introduced, in which case you have an ammonium nitrogen and you nitrify it into nitrate nitrite, and in presence of organic carbon, then denitrify it into the elemental nitrogen. While at Delft, they discovered the shunting process by a very specific subset of microorganisms that takes partial nitritation together with the remaining ammonia and converts it directly through a single biological step into an elemental nitrogen. And that's the fundamental basis of the NMOX technology. So the characteristics is, as I said, partial nitritation. And our specific NMOX technology is relying on the process of granulation of biomass and then our patented systems, two-phase separators for retaining that biomass within the reactors. And so we utilize a single standing reactor with aeration, biological process control, and two-phase separators to effectively remove ammonia within the systems. This is how long we've been in operation and the nitrogen load. We've been in installed basis of the nitrogen load. And the sectors that we've covered are industrial wastewater, digestate rejects, municipal side streams, and many different applications. We have substantially lower footprint, absolutely no reliance or exogenous or endogenous carbon. The yield is relatively low, so the biosolids generation is substantially lower. Because of the partial nitritation, the energy requirement is lower, and also because of the partial nitritation, the alkalinity requirement is also substantially lower compared to the conventional nitrification denitrification systems. And as described, this is as simple as it gets, as long as the biological system is properly designed. And I'll be talking about some constraints. Obviously, as it comes with all engineering systems, we have an operational range where NMOX works the best. But as far as the complexity goes, the only thing we need is a single reactor. And everything else happens within the single one-step system, but with the biomass retention and the conversion in a single stage. This is how the two-phase separators look, and this is the only proprietary section of this, together, obviously, with the know-how on how to operate the systems or how to design and operate the systems. The startup times in early days, because of no availability of the seed biomass, have taken as long as 180 days. And currently, we're able to start up this system, these biological systems, in under 5 days with the proper amount of seeding and the process control. Amazingly, the footprint, you can see comparable footprint, 50% of nitrogen load being treated in a tiny spaces compared to the rest of the facility. And that's all thanks to the specific design of the system and the two-phase separators retaining the biomass at very high concentrations, which allows us to run at substantial nitrogen loading rates compared to any other biological system removing nitrogen, including other NMOX technologies. It's very important to note that because of the simplicity of the controls, we are not restricted to a certain geometry. And so the NMOX can be installed in above ground circular tanks, in-ground concrete tanks, above ground concrete tanks, rectangular or circular. So it completely doesn't matter how the geometry is set as long as we can do the design. This is straightforward. I always like to do a really quick shout out to the FOSPAC technology when I talk about NMOX, because this is a marriage made in heaven, specifically when we talk about the solids and RNG space. Vast majority of the time, in presence of high ammonia, you also have high phosphorus. In anaerobic environment, phosphorus is also converted to ortho-P. And FOSPAC technology fits really neatly together with ammonia technology because it allows us to recover a magnesium ammonium phosphate, struvite, which partially removes the ammonia, substantially reduces the ortho-P that could actually be problematic for NMOX systems, generates recoverable fertilizer product, reduces the ammonia load for this further step for nitrogen removal, and actually addresses some BOD questions that I'll be discussing as well. and they can be co-located, let's say, in a concrete system, in concrete reactor, right next to each other, and utilize very similar solid separation steps. And this is an example of the Astro separator removal technology that we utilize for the FOSPAC systems. The FOSPAC has been in running also since early 2000s, and we have many installations that go together with NMOX technologies and independently that are treating the phosphorus on a continuous basis. For the industrial applications, NMOX fits into the food industry, potato starch, fermentation, MSG distilleries, animal byproducts, rendering plants, gelatin, poultry, fish, dairy products. We have a substantial reach and substantial knowledge when it comes to installations like this. Here's a municipal case study for the co-digestion in Fond du Lac in North America. I tried to cover multiple continents and applications for the ammonia removal. We had a winter startup, and actually the 5-day startup example that I used before was from this application. And we're treating up to 40% of nitrogen load in a tiny space comparatively. This is a beautiful video of operational system that you can see, and we will be pulling some biomass in a second, but it's always nice to see this two-phase separators within an open concrete tank, how simple it is, how straightforward it is, and how compact this is. And a beautiful, beautiful video actually from our friend Paul showing how beautiful the granules look. To me, it's an absolute marvel of biotechnology. And they do all the work. We should be grateful to the biomass for doing all the work for us. Effluent quality, because of the yields and because of the limitations of the kinetics of the NMOX systems, we get to approximately 50 milligrams per liter. We cannot get too much lower than that, so it's an important limitation to discuss. And the FOSPAC, we can get down to 15 milligrams per liter of Ortho-P phosphorus, not to be confused with Ortho-P itself. With the long-term operational examples, all I wanted to highlight is reliability and stable operation at variable loads. If you don't take away anything else out of this application, I would like to show you the longitudinal data that I'm presenting here. Obviously, and you see it in sales presentations quite a lot, right? People present a graph of, let's say, 4 hours operation showing a really, really good operational window. Here for the Fond du Lac installation, this is coming up of 500 days. And by the way, this data too, we have extended to this day of continuous operation under variable loads, continuous, really, really good performance. This is Darling Ingredients in Netherlands, and this is a rendering application. 2,500 continuous operational days under extremely variable loads of influent ammonia. Very, very consistent application with some very, very rare occasional upsets for the system. Similar application for a dairy application where a loading rate is all over the place, very consistent application for thousands of days in running. As with any engineered system, it's extremely important to recognize that this is not a magic pinky dust that will solve all of your problems. It's an engineered system that could be engineered to fit into your solution. And the most important thing is we know how to do this because we have years and years and years of experience. A few things to highlight, right? If there is a substantial amount of the BOD carryover, we need to address it. That's where FOSPAC actually also fits relatively well, because through an additional aeration, you'll also be degrading readily biodegradable BOD. High TSS carryovers will need to be pre-treated, and you can control it with our AstroSense separators, which can control the biomass retention quite well. High ammonia inhibition at high pH, right? And the pH, an ammonia pH equilibrium was discussed, so something to be talked about. Polymer overdose, especially when you have, let's say, a centrifuge, which we recommend in majority of the applications because of the high TSS coming in. we need to really be mindful about protecting the polymer carryover. And orthopy, we discussed ad nauseum when we discussed the fastback application. So the long-term outcomes, extremely small footprint, very, very high comparative nitrogen loading rate, extremely high ammonia removal, very, very energy efficient, and lowest overall GHG emissions for nitrogen removed, as far as we know. And this is it.
Wonderful. Thanks, Timur. Wonderful technology there, Animox, as far as energy efficiency and lowest total life cycle. So we've got some time for questions, so I will hit some of these. Timur first, upper ammonia limit for Animox, approximate.
Approximate upper ammonia limit for Animox on a single stream treatment is 2 to 4,000 milligrams per liter. We can go higher, but that will require either external or internal dilution, depending on what's going on for the rest of schematic. We've treated as high as, let's say, 7,500 milligrams per liter of ammonium nitrogen, but then you need to make sure that there is a post-aeration step with an internal recycle to pre-dilute, because it's not the nitrogen load that is the problem, it's the approach concentration of ammonia that can inhibit biological activity, and as long as we manage that, we can go relatively high.
Okay. Jan, how about potential for scaling in your system? Can you speak to scaling, please?
Yeah, I saw that question also. Struvite scaling does not happen inside the columns. That is because of the special design and the material that we make, but it happens in the heat exchanger, and there it is controlled. And since in most cases we do not work with an alkaline agent, it is controllable. And in case you do, you need to clean more often. And for that reason, we have developed CIP systems, clean in place systems, to clean the heat exchanger, and also the stripper can be cleaned, but in those cases it's not struvite precipitation, but it's mainly organic residues.
Okay. How about percent dry matter? In your data, you showed 42% as that was recovered dry matter, right? How about in the dry matter percentage in your feed material?
It is not well. We have operated stable with 12% dry matter in the past. It's not typical that we do that. Actually, it's the limiting parameter is more the viscosity, because the higher the viscosity, the lower the stripping efficiency is. So we can take in very viscous streams, but you have to take into account that you might need larger stripper systems.
Okay.
Particle size is another thing. So we can take in particles as big as 12 millimeters.
Mm-hmm.
But if you want to apply heat recovery, then the particle size has to be smaller.
Okay. Timur, how about the use of Animox in a cold climate?
Animox can be used in the cold climates. It's highly dependent, obviously, on the temperature of the influent water. Most of the time, Animox in our industry is on a effluent from anaerobic digestion, most often operated at mesophilic ranges, let's say 35C. And so at that temperature range, we have absolutely no problem. So as long as you have proper temperature control coming out. If we're talking about direct stream treatment for ammonia, at which case we're operating at ambient temperature, then definitely the heat addition will need to be discussed.
Okay. Jan, some questions about heat exchange, heat recovery options, tube heat exchangers, spiral, plate. What kind of options do you have for heat recovery?
Actually, we have our own make. Those are tube and tube heat exchangers. And in most cases, we deliver them because we have a modular design. They're very easy to clean. But in case a customer wants something different, then we can offer the stripper without the heat exchanger.
Okay. Very well. So we're at time, and any other additional questions, the contact for Jan and Timmer will be on the slide decks. You can download. You're going to get the link again. It'll come through on over the weekend. So actually, no, Thursday. Thursday, you'll get an email from me with the links. So just want to thank Jan and Timmer for their presentations, and I thank all of our remaining 115 guests for your time and for joining us today. Hope you found it beneficial, and give Jan and Timmer a call if they can give you some support. Stay tuned for next webinar, and with that, we are wrapped up. So long, everybody.
Huge pleasure. Thank you so much, Paul.
Thank you, Paul, and everybody for attending this session.